Welcome to section 5.4, the definite integral. Today's goal is to calculate values of definite integrals using our properties. So we have the following theorems. The limits of left and right sums is if our function is greater than 0 and is either increasing or decreasing on the interval from a to b, then its left and right sums approach the same real number as if n were going to infinity. Our next theorem is the limit of Riemann sums. If f is a continuous function on our interval from a to b, then the Riemann sums for f on this interval approach a real number limit I as n goes to infinity. And we'll look at how these theorems specifically look at in examples here in a minute. The definite integral is if f is a continuous function from a to b, the limit I of Riemann sums for f on this interval is our definite integral of f from a to b, and we will write it as our integral, and you can see here now we are putting values on our integral, and it's going to be denoted with this integral from a to b. So this will allow us to make the definite integral instead of the indefinite. So we won't be using plus c anymore. We will find what our integrals are on these intervals. Here are our properties that we'll be using today. The integral from a to a, so from the number to itself, is going to be 0. This should make sense because if you're imagining the area under a curve and we are only at one point, we don't have any area. The integral from a to b of our function is the negative version of b to a. And then our integral from a to b of a constant times our function, we can pull that constant out front and then take the integral of our function. The integral from a to b of two functions, the sum of them or the difference of them, we can split that and take the integral of each one individually. And the integral from a to b of our function, we can break into smaller integrals and take the integral from a to c and add that as the integral from c to b. So we can break it up and take the sums. In problems 1 and 2, calculate the indicated Riemann sum, and that will be denoted with s sub n for the function f of x equals 7 plus x squared. Okay, number 1 says partition from -1 to 9 into 5 subintervals of equal length. And for each subinterval from x sub k minus 1 up to x sub k, let c sub k equal this x sub k minus 1 plus x sub k over 2. So we're finding the intervals that we're going to be breaking this into. So we're looking only at -1 to 9, and we're breaking it into 5 intervals. Okay, so first I'm going to begin with my change in x, or my delta x. And this is going to give us, we are finding from -1 to 9, and we want to break it into 5 subintervals of equal length. So in order to do that, we need to find our difference, 9 minus -1, and we're dividing it into 5 equal groups. So this is going to give us 10 over 5, which we know is 2. And now let's find what these different intervals are. So our first one, c sub 1, is going to be -1 plus 1 over 2. And where did this come from? Well, it came from what they told us to use right here. X sub k minus 1 plus x sub k over 2. Okay. This is giving us 0 for our first break. So the first interval will be from -1 to 0, and then we'll have 1 plus 3 over 2, so that will take us to 2. And then next we'll have 3 plus 5 over 2, which will give us 4. And then we'll have 5 plus 7 over 2, which will give us 6. And lastly, we'll have 7 plus 9 over 2, which takes us to 8. Okay, so now we've got each of our C sub k's. So let's plug these values into our function and find out what our function values are. So at 0, what will we have? F of 0 equals 7 plus 0 squared. So that gives us 7. At 2, f of 2, we will have 7 plus 2 squared, which will give us 11. At 4, f of 4, we have 7 plus 4 squared, gives us 23. At 6, we have f of 6, 7 plus 6 squared equals 43. And at 5, oh no, not 5, I'm looking in the wrong place. At 8, f of 8 is 7 plus 8 squared, so 71. Okay? And a sum is telling us to find out what happens if we add them all up. That's the sum. So our sum, our S sub n, we're representing with an S sub 5. We have split it into 5 subintervals. And to calculate our sum, we'll have our function at C1 times the change in x. And the reason why we're going to be adding each of these products together is because if you imagine I'm taking the integrals of some kind of curve, we're going to be measuring these points and we're calculating the areas of each of these rectangles. So one of them needs to tell us the point on the function, and the other one needs to tell us the width. So that's the change in x. And by multiplying those two, we get the area of the rectangles, and when we add all of the areas of all the rectangles up, we get an approximation of what's the area under this curve. So we'll continue to add all of our function values times our change in x until we have all 5. And this is represented by, okay, we calculated f of C1 was that f of 0, so we have 7. Our change in x is 2. Plus that 11 times 2, plus that 23 times 2, plus the 43 times 2, plus the 71 times 2. And this will give us 14 plus 22 plus 46 plus 86 plus 142, which gives us a sum of 310. And that's going to be our process here. Okay, partition -4 to 8 into 4 subintervals of equal length, and for each subinterval, x sub k minus 1 to x sub k, let c sub k equal 2 times x sub k minus 1 plus x sub k over 3. So you may have noticed right away, okay, calculating our c value is going to be different than number 1. So pay attention to those. Okay, let's first find our change in x value. So we have from -4 to 8. So we've got 8 minus -4, and we're splitting it into 4 subintervals. This will give us 12 over 4, so we've got 3. Now let's find each of our c values. So we have c sub 1 is going to be 2 times x sub k minus 1, that's our -4, plus x sub k, that's our -1. Oh, no, yeah, our -1. And it's divided by 3, it says. And how did we get that -1? So we are changing our x by 3. So from one interval to the next, that's where that came from. This was going to give us a -3. Our c sub 2 is going to be 2 times -1 plus 2 over 3, giving us 0. Our c sub 3 is going to be 2 times 2 plus 5 over 3, giving us 3. And our c sub 4 is going to be 2 times 5 plus 8 over 3, giving us 6. Let's find the function values at each of these. We have f of -3 will be 7 plus -3 squared, giving us 16. F of 0, 7 plus 0 squared gives us 7. F of 3 is 7 plus 3 squared, giving us 16. And f of 6, 7 plus 6 squared gives us 43. Now let's find our sum. We have s sub 4. Remember, we're looking at the function value at each of these times our change in x, and we're adding all of these up. So what are these values that we have found? We have 16 times 3 plus 7 times 3 plus 16 times 3 plus 43 times 3. This is going to give us 48 plus 21 plus 48 plus 129. So total, our sum comes out to 246. In problems 3 through 7, calculate the definite integral, given that the integral from 0 to 6 of x dx is 18, the integral from 0 to 6 of x squared dx is 72, and the integral from 6 to 9 of x squared dx is 171. So hopefully we'll be able to use this given information and that property that allows us to break up integrals to find these definite integrals. The first one we're looking at is the integral from 0 to 4 of 3x dx. And that is a typo. We don't have 4. It's going to be 0 to 6. I apologize. Now, I'm going to begin by using one of our properties from above and pull that constant 3 out in front. So we have integral from 0 to 6 of x dx. And that we know the value of. So we will have 3 times 18. And that is just 54. Okay, next we have, let's take this with us actually. The integral from 0 to 4 of 2x plus x squared. And again, it says 4. It's supposed to be a 6. Okay. So let's use the property that allows us to break each one of these into their own. So we have the integral of 0 to 6 of 2x dx plus the integral from 0 to 6 of x squared dx. And then I'm going to pull that constant 2 out front. So we have the integral of x dx and the integral of x squared dx. And now we can use the values that we've been given. So we have 2, and the integral from 0 to 6 of x dx is 18. And then the integral from 0 to 6 of x squared dx is 72. And 2 times 18 plus 72 will give us 36 plus 72, totaling 108. Okay, number 5, not 0 to 7, 0 to 9. The integral from 0 to 9 of 2x squared dx. Let's begin by pulling our constant of 2 out front. 0 to 9 x squared dx. And then, because we have values that go from 0 to 6 and then from 6 to 9, we can use our property that we will be adding from 0 to 6 x squared dx to the integral from 6 to 9 x squared dx. Those are the ones we have properties to, and it spans the whole interval from 0 to 9. So we have 2 times the integral from 0 to 6 x squared dx is 72, and the integral from 6 to 9 x squared dx is 171. This will give us 2 times 243, totaling 486. Number 6, the integral from 6 to 0 of 7x dx. So first, I want to pull that 7 out front, 6 to 0 x dx. And I don't have any integrals that go from 6 to 0, but I do have integrals that go from 0 to 6. So I'm going to use the property that makes the negative version and flips our interval. Now I can use what we've been given. So we have negative 7 times the integral from 0 to 6 x dx is 18. And this product gives us negative 126. Number 7, the integral from 7 to 7 of x squared plus 2x minus 15 dx. Now, remember, when we go from the place to the same place, here in this case we're going from 7 to 7, the value of the integral is 0.